My name is Marc Goodner. I'm a product manager on the C++ team at Microsoft, and I'm here today to talk about overcoming embedded development tooling challenges. And so we'll dive in. At CppCon, there's a lot of us from Microsoft here. We actually have a link to a Discord server there where you can find anybody from the Microsoft team to ask questions or discuss any of announcements with us. We've also got a survey that's important to us for attendees from the CPP community. If you could have a chance to take that survey, it would really help us out in terms of prioritizing product features. I mentioned I'm a product manager on the C++ team. I focus on embedded across Visual Studio and Visual Studio Code. And what I wanted to talk to you today about is overcoming embedded tooling challenges. And to do so, I think we're going to start with covering kind of where embedded tooling is today. And then from there, I want to focus on using your own IDE for embedded development. I think that's really kind of the biggest challenge in terms of, the complexity of embedded tooling out there is how do you use your preferred IDE? And so in terms of preferred IDEs, I'm going to focus on CLion, Visual Studio, and Visual Studio Code. Those are the ones that come up the most frequently in terms of IDEs that we see correlated in surveys across the industry with C++ embedded development. There's some other ones that are also popular, but they seem to be declining. These are the ones that seem persistently popular or rising in popularity. And then I'm going to close with some discussion of continuous integration, like how can you take the project that you were using in your preferred IDE and then get it into a CI system. I want to, at the beginning, kind of cover some things that I'm not going to cover. So if these are also embedded tooling challenges or embedded challenges you may be having, but this talk isn't really going to cover these topics. First, I'm not really going to cover the cloud, so I'm not going to cover AWS or Azure or anything else from that perspective. Those are big topics, but that's not what I'm going to be talking about. Nothing about those SDKs or anything. I'm also not going to talk about C++ really, or other languages. The focus of this talk is really more on the tooling than the language itself. And so similarly, while we'll look at some stuff related to RTOSs, we're not going to talk about like free RTOS versus Zephyr or other RTOSs. And also, not embedded Linux. Embedded Linux is its really own topic area. This talk is really focused on tooling at the Cortex-M level, so really where the RTOSs play or super main loops and that sort of stuff. Testing does fit into CI, and so there may be a few words about that in the context of CI, but testing embedded applications themselves, like what embedded framework or what testing framework is good for embedded, is also something I'm not really going to spend any time talking about. So with that, let's get going on where embedded tooling is today. I think the best place to start is really to kind of look at the survey of silicon vendors and what are the sort of tools that the silicon vendors provide. And so this is kind of the survey of the silicon vendors whose tools I took a look at in preparing for this talk. I spend more time with some of them than others myself, but this is kind of the group that I looked at for the talk to kind of look at their tools and see what they provide. Obviously, this is not all the silicon vendors. There's a lot of silicon vendors out in the marketplace, and I think that a lot of them have similar tooling strategies to these companies, so I don't think that you'll find anything too surprising if you're using another silicon vendor of what I'm going to say about these folks. So when we look at the silicon vendors, they all have a bunch of tools that they provide. We can kind of start by looking at most of them provide an IDE. I think the exception to this is Espressif. I haven't seen an IDE from Espressif, but they do have a very rich CLI environment for configuring their environments. Most all of them have a compiler, and even in the case of GCC, it is true that many of these compilers that are GCC are not necessarily straight GCC. They may be versions of GCC that are tailored for that particular silicon vendor. So while you can go get a generic ARM GCC compiler, it may not be the same as what you would get if you got the GCC compiler from your silicon vendor. And as you can see, a lot of them actually have proprietary compilers that they make available as well. From a flashing perspective and debug perspective, many of them have their own flash tool. That makes sense because they understand, how to talk to their own hardware. And they have configurator. These configurators are tools that help with tasks like pen mapping, setting clocks, perhaps even generating source code based on those settings so that you have a starting place for a project. And then in terms of the projects themselves, what you see is most of these, because they're in IDEs, they're Eclipse projects. So if you want to use something outside of the context of the Eclipse IDE that's provided, then you're going to need to get it into another sort of build system like Make or CMake. So looking at across this, what we see, a few of these vendors actually do provide some direct Make support. A lot of the others, if they have an environment that is Eclipse based, then what you're going to find is that you will be able to export an Eclipse project as Make files, and we'll talk about that in just a little bit. And then from the perspective of CMake, definitely CMake is, I think you're going to find in this talk, is the direction you should be going. You don't find a lot of direct support for CMake today. NXP does support CMake directly out of their SDK. Espressif also uses CMake, but I mentioned that they have that rich CLI tool that kind of helps you target their devices, and that kind of wraps CMake, but you can use CMake directly with their products as well. And so why, I think looking at this, you can kind of understand why these silicon vendors produce their own IDEs. Because it's a convenient way to take all of these tools and package them up into one environment that they can then distribute to their customers. But it then becomes difficult if you're trying to use a different IDE, or if you want to integrate this with the CI system. It's maybe not the best to get your tools as an IDE. But from a silicon vendor perspective, especially historically, this is a good way to kind of package everything up. And so that's kind of why we're in this situation where everybody kind of has their own IDE. So in terms of the projects that you get from your vendor, I mentioned already that most of the vendor IDEs are Eclipse CDT based. And so if you want to get out of there, or if you want to get your project into a CI system, you can go under Project Properties and unselect Generate Makefiles automatically. And what that'll do is actually emit the makefiles, into the project structure, and then you can actually use this outside of the context of Eclipse. So that's kind of one way that you can start getting your project ready to use perhaps in another IDE than what you're getting from the vendor. Many of the project configurators do support other targets. As an example, ST supports ARMGCC with Makefile. I believe when you generate that one, that is actually targeted at the ARMGCC compiler, the generic one. And then you can also look to the SDK samples outside of the IDE. For example, NXP, you can download an SDK that contains projects for CMake, CLion, and IAR that are all for the same source code base. And we're going to take a look at that in just a little bit. And then, moving on, mentioning IAR and CLion, these are two embedded tool vendors that have specialized tools for the industry. What's interesting about both of them is that they have optimized compilers, so they have compilers that are very optimized for producing good code for embedded targets, and so a lot of people choose these tools specifically to get those compilers. But their IDEs also have a lot of hardware-aware debugging capabilities, and I should emphasize that a lot of the vendor IDEs do too. So these are kind of some common tools that you'll see in an embedded IDE that you wouldn't find in a general-purpose IDE. Things like peripheral views to access the registers of the peripherals to see what's going on at the hardware, RTOS-focused views to see the thread view of the RTOS tasks to see its view of the world, which you couldn't get by just looking at like the stack. And then you've got serial and SWO monitors, and then there's a lot of tracing capabilities. And ARM, CLion, and IAR both have some pretty advanced tracing capabilities for trying to map out signals, especially if you're trying to do things, mapping hardware signals with instruction level tracing. The other thing is both of these vendors have some safety certifications, so their compilers may have safety certifications that are relevant to your industry. So you may find yourself in a situation where you have to use these. And then finally, there's CMSIS support. Both of these IDEs provide the ability to bring in CMSIS packs that come from the silicon vendors that have capabilities for the hardware targets. And a lot of the vendor IDEs also have CMSIS support, even in the SDK. So CMSIS is something that you're going to find in almost any embedded project that's coming from the silicon vendors or from CLion or IAR. And with that, kind of looking maybe ahead a little bit, of what's common in the current embedded space is Open-CMSIS. So CMSIS is something that was a specification that came from ARM that all of the silicon vendors used to package up libraries, to package up board support files, and all of this sort of things. And it also had specifications for things like SVD files to get a common view of the peripheral registers. It's really focused on reusable components. And so what Open-CMSIS is it's a new effort to try and evolve the CMSIS specifications in the open. And so ARM and other silicon vendors like NXP and ST are there working on these specifications in the open. And so they're evolving, what CMSIS packs are, for packaging sources and libraries, templates, example code, all of the device information necessary to target it, and startup code, etc. But there's also tooling happening there. So they're working on project generation, and they're working on how you can generate CMSIS packs and build projects based on that. And so this is an interesting project. It's going to come up a little bit later again, but this is something to definitely keep an eye on if you're in this space. But with that, let's get to the heart of this, and let's start talking about how you can use your IDE for embedded. But first, we're going to take a quick diversion into CMake and Vcpkg. So for CMake, my recommendation is that you go find some embedded specific examples for CMake. There's a lot of commonalities you'll find when you look at CMake projects for embedded. One of those is using toolchain files. Toolchain files are a CMake script, if you will, that kind of collects common compiler options together. So this gets these compiler options out of the path that you may emit to GCC, but gets them into the CMake file so that you have some reproducibility there. And then the other thing I would recommend, and is not always done, but I would recommend that in your CMake files you find your compiler on the path. So set your compiler on the path as part of your environment, and then in the CMake file detect where it is at runtime. That allows you to switch between different compilers. I would say definitely don't rely on hard-coded paths. It's pretty common to see people use environment variables to detect where the compiler is, but I think finding it on path is a little more flexible, and we'll see why in just a second. And then finally, CMake presets. Definitely use CMake presets to capture your options. CMake presets are really easy to use with the CLI, and they're understood by the IDEs we're talking about here today. And so you'll find a lot of times when you look at embedded CMake projects, you'll find that there's bash scripts or bat scripts or something that are invoking CMake with a bunch of options at the command line in order to configure the project. What CMake presets do is take a lot of that stuff that would have been in a script and instead get it into a JSON file so that it's more reproducible and easier to use consistently with CMake. So that would be my recommendation. Now Vcpkg, we recently introduced a new thing to Vcpkg, and I say we because this is a Microsoft open source project, but called artifacts. So Vcpkg is something that has been used, it's used for library management for C++ projects as a concept called ports. We added a new concept called artifacts, which is basically a set of packages for a developer environment. The artifacts may consist of things like compilers, linkers, build systems, or SDKs. And then there's a project manifest that captures all of these dependencies necessary for the project that you can then use to activate the project and place all of those dependencies onto the command line. This was something that was designed with embedded in mind. Because we saw a challenge. I mean, in terms of the vendor IDEs and everything we're talking about already, it's very challenging to bootstrap an embedded developer environment. So if you want consistency across your team, you want a consistent way to get the tools to everybody in the team and into your CI system. And so we designed artifacts as a way to accomplish that. And then as we started taking a look at the broader C++ ecosystem, we realized that this was a broader challenge than just embedded, and so that's why we brought it into Vcpkg as a generic concept as opposed to something specific for embedded. Today, most of what you'll find for Vcpkg artifacts is kind of focused on embedded, but we'll expand that over time. So I want to give a quick demo of what this looks like at this point. So what I have is a project that actually comes from a NXP SDK for a simple free RTOS project. And it's targeted at the LPC 55S69 board, which I've got attached to my PC here, as well as a COM port for serial. This project was generated from a CMake template that was based on a project from MCU on Eclipse that was showing how to use CMake projects and get them back into Eclipse. But what I did was took that project and kind of added some stuff to show how you could do CI and GitHub Actions, as well as use it with Visual Studio and VS Code, and modified it to use Vcpkg artifacts as well as CMake presets. And so this template you can use to generate your own repo without having to worry about upstreaming things back. I then used that repo and kind of modified a NXP sample we're going to look at in a little more depth in a little bit. But if we go to the command line, this is where I have my free RTOS project locally. If we just take a quick look at what's here, I've got some dev container stuff, I've got my GitHub actions, but really what I want to talk about is, you know, the CMake presets.json, the Vcpkg configuration, and the toolchain. So first, if I take a look at the Vcpkg configuration, this is the manifest I was talking about. And so this manifest is pretty simple. When you create a manifest with Vcpkg, it adds a connection back up to the source registry for where you get the port files from for your libraries. But this registry is an artifact registry. And so this captures descriptions of things like CMake and Ninja and GCC that I can add to my project. And then what I can do is check this file into with my project, and then from the command line it will recognize it. I can activate the project, and if I don't have these dependencies, it will reach out to the registry, find out where those dependencies are. We're not rehosting them, it's just a registry that points to the location where they actually are, and then pull them down to activate for use on the command line. And so then for CMake presets, we take a look at this, you can see CMake presets are a little JSON file, and we can see things that you, I'm sure, would be familiar with for CMake in terms of looking at like what the generator is that we're using Ninja, setting where the directories are for our generation, and setting up, you know, where our compiler or what our compiler is, as well as debug and release configurations. And finally, I forgot. So the other thing I wanted to highlight here was the toolchain path. Yeah, there's our toolchain path, sorry. So there's our toolchain path, which is normally something that you would pass on the command line. And in this case, our toolchain is right in the directory. And so if I take a quick look at that, oops. So we take a quick look at this. This is what I was talking about detecting your toolchain on the path. So there's a function in CMake where you can say find program and express what the program is you're looking for. And here, you know, this is actually pretty typical in most embedded projects for CMake. You'll see setting the toolchain extension for whether it's exe or not, if you're on Windows or not, and then what the target triplet is for GCC. But so you can detect the location of that on path, and then you can use the file name component to get just the path location of that, because you're going to need to set this to set up, you know, things like where the location of object copy is, or the size tool, or other things that you're going to need. So that's a pretty convenient ability. So let's take a look at how Vcpkg works here. So to get Vcpkg on my command line, there's a little script that I can run that initializes it, so it's not actually on my path until I run this. So that dot sources Vcpkg into my environment, and at this point I can say Vcpkg activate. And so I have already activated this project before, so it runs really fast and gets these things onto my command line. If I hadn't initialized this in the past, it would have reached out to the internet and pulled these tools down. And now I've actually got CMake available at my command line, and I can say list presets. And so you can see there's the presets from the file, and so now I can say CMake, and I can run the configure step for my preset when I want to do M33 debug. And so just like that, I've got everything necessary, you know, to configure this project. And to build, all I need to do is emit the build command for the build preset, and then that runs and builds. And the CMake list actually use those tools to emit the size information for the image. So that's pretty great. I mean, that's how quickly you can actually bootstrap a dev environment using Vcpkg. But, you know, even if you're not using Vcpkg, a lot of those CMake tips of using CMake presets, detecting your compiler, those are still valid whether or not you're using Vcpkg. And so with that, let's get back to the presentation. All right. So yeah, so what we saw was initializing Vcpkg. The project I was using was a Git clone of that project there. And I will have, at the end of the talk, there will be a link to everything, a bunch of resources that I've used in this. So there's plenty of references to look at the end of the talk. But I've activated my project, which put my compilers, it put Ninja and CMake available on my command line, and then I was able to run CMake for the preset and build. And there's some simple one-liners to install Vcpkg if you don't have it installed. So let's get talking about our IDEs now that we've got that as a little bit of background. The reason I emphasize CMake so much is because CLion really favors CMake as its build environment. And when you look at CMake and embedded, you'll find that there's been a lot of work in CLion for some time to support embedded. JetBrains provides example CMake projects for embedded that you can take a look at that work with their environment. One of the key things is making sure that you set your compiler on path. So there's the path within CLion in terms of where you need to set your toolchains up. They document configuring for ARM GCC as well as IAR. On Windows, the IAR support does require MSIS availability on your local Windows box. I believe because they're using the IAR actually has CMake documentation that's focused on build environments, so it's kind of Linux focused. So using IAR with CLion does require that you have MSIS available. And then they also have a STMicro project importer, or STM32. This requires that you have the STM32 Cube product installed on your local machine, as well as an ARM GCC toolchain. But that provides the ability to generate projects in ST's project configurator, get everything set up there, and then generate your project, and then you can actually edit the code in CLion instead. They also support other build environments, so you don't have to use CMake. I would strongly encourage you to use CMake, but they do support Make, and they have the ability to use custom build systems as well. So if we look at Visual Studio, CMake again, we've added embedded capabilities as part of Visual Studio 2022. What you need to do is add the Linux and embedded workload. And then our team has made example CMake projects available for embedded that you can find. There will be references for the talk. All of those examples use Vcpkg for activation of the tool chains because we don't want to distribute the tool chains as part of the IDE itself. We want to build an ecosystem of making it easy to get tool chains from the providers. And in 17.4 preview that was released yesterday, we added automatic Vcpkg activation as part of Visual Studio. So what that means, if you have Vcpkg installed locally, when you open the project in Visual Studio, it will detect that and it will then activate that environment and use those compilers as part of your project. So Visual Studio Code, again, CMake. So we have a new extension called the Embedded Tools extension. The same projects that we provide for Visual Studio work within the context of Visual Studio Code, and we use Vcpkg activation again for acquiring tool chains and CMake, etc. For Visual Studio Code, what you would do is activate the project from the command line of your project and then launch Visual Studio Code from that activated environment, and then all the tools get picked up and are available to Visual Studio Code. There's also a STMicro project importer that our team has worked on in conjunction with ST. So what this project importer does, you're able to point it in STMicro project. It imports it as a CMake project. We have worked with ST to run this project importer across a library of their SDK projects that cover about 3,000 different projects. We're actually over a 94% build pass rate at this point. We're obviously not able to test this across the depth of ST's devices, but for the devices we have, we've run these. Today, this does require the STMicro Cube IDEs installed locally on your machine. The reason we require that is because we're using this activation and project importer uses the compiler and platform that comes from the STMicro IDE environment. That gives us the highest compatibility to what you would get if you use the STMicro IDE directly. And it also works with STM32 Cube projects if you're using the project configurator from STMicro. Our team has also worked with IAR, so there's actually a official extension from IAR, or two extensions actually. There's a project and build extension so that you can open an IAR project in Visual Studio Code and build it. There's also a debugging extension that uses IAR CSpy, which is not GDB based, but they've brought their debugging capability into VS Code with this extension to integrate the debug information into VS Code. But you don't have to learn new Windows or anything because working with them, the sort of views we'll talk about as we go forward are the same views for generic ARM GCC as they are for IAR in the Visual Studio Code. So debugging. Now once you've got your project in, of course you're going to want to debug. So in CLion they support on-chip debugging. They provide native OpenOCD support, so you don't have to go get OpenOCD. It's part of the IDE. They also provide some embedded specific GDB configurations, so that's the menu entry you would go to add a new embedded configuration under the run menu there. And they actually provide tailored configurations here. So they have tailored configurations for OpenOCD, for JLink, and QEMU. There may be some others as well. But the screenshot here, what you're seeing is the configuration for OpenOCD. And if you're familiar with OpenOCD at the command line, I'm sure most of this looks familiar to you in terms of pointing at a board config file, setting the telnet and GDB ports, etc. So that's their story. For Visual Studio, we also support on-chip debugging. We're using our launch.jsons to configure for the C++ debugger that's part of Visual Studio. We have example configurations for OpenOCD, JLink, and ST-Link. We also support hardware breakpoint limits. A lot of these devices have a limit in terms of how many breakpoints they can support. And so if you exceed that breakpoint count, what can happen is the debugger can become unstable, and you'll need to reset. So what we've got the ability to do in our configuration files is allow you to say how many breakpoints your device supports, and then if you try and set more breakpoints than that, we'll detect that you're exceeding the limit and not attempt to set that breakpoint. That way, the debugger remains stable and you don't run into any issues. Visual Studio Code, similar story. We're using CppDebug, and we've got a launch.json that you would configure there. And we're supporting the same debuggers that from Visual Studio, OpenOCD, JLink, and ST-Link. And we also support hardware breakpoint limits in Visual Studio Code. So peripheral views, we kind of talked about this in the embedded IDE story. But basically, you need to find the SVD file for the board that you're using, and then in CLion you're able to point to that SVD file, and then CLion has a view that will use that SVD file to give you a mapping of the peripheral registers, and so you can inspect the values of those registers while you're debugging, which is something a lot of embedded developers are going to need to be able to do so that they can make sure that things are set as expected and inspect things to diagnose issues. So Visual Studio also has a peripheral view that's new in 2022. Similarly, there's an SVD path that you need to set in the JSON, and once you set that path, there's a embedded registers view that is available from the debug menu. The illustration here is showing before and after step of an impact on the highlighted register there. And then Visual Studio Code, a similar story. There's a peripheral register view. Set it up in the launch.json. And then you've got a view that you can inspect your registers with. And then so CLion, for RTOS objects, CLion has an RTOS view that allows you to get a view of the tasks that are running. So RTOSs, provide kind of their own view of what's happening in their world by creating tasks that the RTOS itself manages. And so you want to be able to, when you're debugging things, be able to look at the different tasks that are running. You want to see what the stack usage is, how often they run, what the priority of these are. And so that's what this sort of a view provides for you. And so CLion has support for both FreeRTOS and for Zephyr. In Visual Studio, there's an RTOS object view as well. A lot of the same sort of capabilities. The RTOSs that are supported in Visual Studio are FreeRTOS, Zephyr, and Azure RTOS, previously known as ThreadX. And then you can see some of the different RTOS objects that are also available in addition to threads. I do believe that CLion also has views for additional RTOS objects. I should have covered that. I usually focus on kind of the thread view, but there are different RTOS objects like timers or queues, etc. And then for Visual Studio Code, it's the same RTOS object view that we have available in Visual Studio, and the same RTOSs available in Visual Studio Code. In Visual Studio, we also have a serial monitor available that allows you to monitor and send data over serial. If CLion has this capability, I wasn't able to find it, so I apologize, but we do have a serial monitor integrated in Visual Studio, and we have the same serial monitor integrated into Visual Studio Code. So with that, I want to break back out to a demo to show kind of what some of this looks like within an IDE context. And I'm going to take a look at that FreeRTOS generic project again, but this time we're going to take a look at it as how it comes from the NXP SDK. So let's pop out of that. And so this is the NXP SDK for the board that I'm using. So there's a whole bunch of stuff in here. We have to drill pretty deep down into the directory structure to find the example that we're looking for, but it's the FreeRTOS generic one here. This board has more than one core. This particular project is for only one core. But you can see here the way this project is organized, all of the source code is kind of in a root directory. And then the project directories are subdirectories of the actual source code. This is not an uncommon strategy in the embedded world. A lot of the IDE vendors, when they support more than one project format, take this approach where the source code is in the parent of the project structure. But I won't go over Vcpkg and CMake again. Needless to say, basically this is a CMake project for ARM-GCC, but what I did was I added the Vcpkg activation here. I also added CMake presets rather than use the scripts that come from NXP. And then I made some small changes to the CMake toolchain file that's in the root of the project so that it would actually detect the compiler coming from Vcpkg rather than requiring me to set an environment variable. And so in Visual Studio, I can point to that folder. That's the folder I was just showing you. And if I open that folder, what happens is Vcpkg activation will start. You can see that down here. So Vcpkg activation has started. And CMake is running to configure the project. And so at that point, now everything's up and running. Visual Studio knows how to build and configure this project. I spent a lot of time talking about the launch.json. This is what the launch.json looks like. So in this example, you can see that for the debugger path, we're just using JLink. JLink is installed on my system, and it's available on the path, which is why I'm able to specify it that way. It's not available via Vcpkg yet. And then I'm passing just the debug server arguments to the JLink server, detecting, that's how I detect that it started. I wait to see that message at the command line. And then after we're connected, there's a couple of commands that will run in order to start the application. Now, you'll notice over here in the Solution Explorer, I don't have any source files, which is kind of annoying because of the way that this project is structured. All I have is my project files. In Visual Studio, you can click this button here, which is gives different views for the project, so I can switch to the CMake targets view. And then when I'm in the CMake targets view, now I can actually see the binary that's produced, and I can see all the files that produce that binary. And so I can expand here, and then I can open up this file, which is kind of the main. And so you can see here, now I'm getting IntelliSense information back, so I'm getting context on the application that's coming from it being properly configured. I can navigate to one of my events that's of interest to me, and I can set a breakpoint here. And now I can select my target and hit go. And now it's going to build my project using CMake, so it's going to produce the same output as if I were to run that at the command line. Now it's using JLink to flash, and we break heading into the startup script. And you can see here the peripheral register view is opened up. I can also go ahead and start monitoring with my serial monitor. This is my serial device that's wired up to my board. And I can hit start monitoring and let this application continue into the app. And there I've hit my breakpoint that is going to start an event. And so if I step over that, well, let me let that continue. And so we can see that this sent 12 messages over serial, and now it's back to this breakpoint that the event task is running. And now if I step over it again, we'll see that message come out. So this message is going out over serial. So that's using that project in Visual Studio. And now if I come back to this project, you'll notice that there's an IAR project here as well. So if I grab this directory and go over to Visual Studio Code, well, let's close all these files. And if I open that folder in Visual Studio Code, I have IAR. This does require that IAR, the application is installed on your machine, so I have that installed. I can now go navigate to that folder and open that up. And now you can see a very similar thing that we saw in Visual Studio, which is the File Explorer is really only showing you these project files. So in order to see the project itself, you need to go to the IAR view, which is going to process their project format. So they're the ones who know their project format, but they're able to use that and give you a view of the project here. and then from there you can actually go over and switch to debug and hit run and debug. And this is going to launch the IAR debugger. So there you can see it's starting CSpy, and now it's downloading the app. And now we're breaking into our main. You can see we've got the same serial monitor available for us here in Visual Studio Code, so I can start monitoring at this point. But it's kind of a similar experience, but what's key is we have the same views in Visual Studio Code, whether you're using GCC or whether you're using IAR. All right, so in review for the IDEs, for CLion, CMake is where you definitely want to go. I advise you to look at example CMake projects out there for GCC or IAR, depending on which one you're using. And they have a ST project importer to get projects from STMicro into the CLion environment. Let me think. Yeah, actually, I should have mentioned they're also using a similar strategy as to what we were doing in VS Code, in which the project import actually generates a CMake project that understands some things about the layout of how the STMicro project is laid out. So it's a similar approach. Even though it's a project importer, it doesn't actually use the project itself natively. It's taking that project and kind of creating a CMake project that understands the things that the STMicro project understood. And then in terms of embedded specific features, there's a lot for CLion. It's got GDB to support on-chip debuggers, so you can debug directly on your hardware. They have views dedicated for peripherals and for RTOS objects, for free RTOS and Zephyr. I didn't cover it in the main line, but they also have some static analysis capabilities. They're claiming partial MISRA-C and C++ support for their static analysis. Definitely keep an eye on their website for that one, because they kind of have a link to a live report of what they're actually covering from MISRA-C and C++. For Visual Studio and VS Code, I'll just kind of cover these together because it's very similar, and our team works hard to make sure that it's similar. CMake preferred, again, and we provide example CMake projects for embedded that you can take a look at. We have STMicro project imports, VS Code only for that one at the moment. And then we also use Vcpkg artifacts for all of our toolchain acquisition. That's really our preferred approach for getting things onto path. In terms of embedded specific features, we've got on-chip debugging, so you can actually debug directly on your hardware, peripheral views for ARM devices, as well as RTOS object views for free RTOS, Azure RTOS, ThreadX, and Zephyr, and a serial monitor. And we have there's a VS Code extension for IAR projects. If you're using IAR, you can actually use the VS Code environment for those projects, and that's from IAR and supported by IAR. Now, before we move on to talk about CI, I think there's a couple of notable other modern embedded IDEs that's worth mentioning. One is CLI Studio. So CLI Studio is a cloud-based IDE that ARM is working on that is Open-CMSIS based. And so this actually supports even device debugging over WebUSB. So from a cloud IDE, you can actually point it and tell it what target hardware you're using, and you can actually edit all of your code in the browser, build your project, and then actually flash all the way down locally to something attached to your PC. And so it's an interesting approach, seeing where this is going, but it's also a real good test case for the Open-CMSIS project, because everything here is the project format and everything that they're using is using the tools that are coming from that Open-CMSIS project and the project file format. So that's definitely an interesting one to keep an eye on. And then the other one I want to mention is PlatformIO. So PlatformIO is a really interesting system. It has a kind of a core CLI, and that core CLI provides a lot. It has its own build system, it's got a package manager, it's got capabilities for library management, serial port monitors, debugging, unit tests, and this is all kind of in this core CLI that comprises the system. And it supports a lot of different silicon providers, and it provides support for a lot of different platforms like Arduino or other kind of frameworks, if you will, for embedded. It also supports IDEs. They have a VS Code extension that you can use that pulls down the core CLI and gets everything running in VS Code. And they also support CLion. And they also have CI examples. So there's a whole bunch of examples that show how to use this system in CI. The thing about PlatformIO that as you evaluate it, you need to pay attention to is the build system. because it doesn't use CMake. It has its own build system. And so when you buy into the PlatformIO kind of ecosystem, you need to come into their build system. And then that build system is really only understood by PlatformIO. But there's a lot of benefits to this system. So if you're looking for something in the embedded space to target a bunch of platforms, it's definitely worth a look. And if I were to advise you of where to go to look to find examples around PlatformIO, I would suggest home automation. There's a lot of examples of PlatformIO for custom hardware or for targeting lights and that sort of thing that integrate with Home Assistant. So that's if you want to kind of evaluate this in kind of real-world applications, that's what I would suggest that you go look for. So with that, let's move on to CI. When I first started working on this talk, I actually kind of was going to have a little bit of a rant almost about, the lack of examples out there, particularly from silicon vendors around CI/CD examples. I had to eat my head a little bit because I found this diagram from Microchip. And this is a pretty good outline of a CI system, and they actually provide, Microchip does, as part of their IDE environment, a CI/CD wizard that actually helps you produce the artifacts necessary to take your project and get it into a CI system. So they have their build tools are available as images that you can use to create containers to build your projects in, and then you can integrate that into your CI system. And then from there they have static code analysis checks for MISR, etc., and even simulators, or at least documentation on how you could try and start setting up simulators and capture the output of your build system in repositories. So this is actually pretty cool that that you've got that sort of support coming directly from a silicon vendor. IAR also has documentation out there on using the IAR compilers in containers, so that once you get things into a container, from there you'll be able to integrate it into the CI system of your choice. And then the last thing I would highlight is just kind of the sample from this talk covers some of this. So what I want to show you is the project I was showing earlier. We'll use this one, which is the CMake template. So this CMake template, I have a Docker file that's part of this. And this Docker file, what I want to highlight to you about Docker files is the reason you want to use Docker or use containers for your build environment as part of CI is just reproducibility. So this is really, and most CI systems are going to support containers. So even though I'm showing you GitHub, containers should work well in almost any CI environment. But what I want to highlight is kind of layers, and you want to use multi-stage containers. And what multi-stage containers means is basically naming the layers. So you can say from, and then you have the base container that you're getting. It could come from Docker Hub or something local, or in this case I'm using a base image that's coming from the Microsoft Container Registry. But I'm naming it as dev. And then what happens is there's a bunch of steps I'm running to actually prepare this container. So when I build this container image, all these steps are going to run. But then what I can do is I have another layer which is from dev as build. So this build stage is coming from this dev stage. And what's important about that is that later on I can use this dev stage, I can target and build a container image just from this dev stage, and then I can use that kind of interactively for development. But I have all of my project assets in here that are necessary to build my application. And then the build stage is really, all that stage does is it uses that base layer, and then it just runs the commands to pull in my source control, or pull in my sources, and then basically just run Vcpkg to get my tools activated, and then run CMake to build, and then then the container would just exit, and I would have my build output. And so the challenge you're going to have with containers is getting your tool chains into the container. So in this case, like what I'm illustrating here is how to get Vcpkg into the container, and then copying my manifest file into the container, and then basically running Vcpkg to activate that manifest, and then pull in all of my dependencies. If you're using anything else, you're going to have to look for guidance from the tool vendors on how you could get those tools into a container to use, and that there might be some challenges there depending on who your tool vendor is. And then once I have that, in the context of GitHub, there's the workflows that you can set up for CI. And so from here, there's just a couple of simple steps, and basically what I'm doing is anytime there's a pull request, this will kick off and run. And what this does is it basically spins up a container by building that target that I mentioned there. So I can say target build, and then that will run and exit once I spin up a container based on that. And then what I need to do is copy the build output and copy that into a location into the host environment that's running the container. And from there, I can actually use these steps to upload artifacts. So I can grab out of the workspace where I saved things, I can grab out of the build output directory and copy my binaries and make them available. And so what that looks like in context here is under GitHub Actions, we can come through and look at a CI run. This is a CI run that ran with that script. And so you can see here that this is the job that it ran, and there are my artifacts. If I select that, it's going to download a zip file that contains my firmware. And so that's pretty great. And so now I've got to reproduce. I can at least, on any push to my repo, I can actually build the firmware and at least make sure that things are building, which is pretty great. Now the other thing I wanted to talk about is security. Under the security tab on GitHub, there's this code scanning capability. And so you can enable that. Right here, I've already enabled it. But you can come in and click code scanning and click enable. And when you select that, what that's going to do is it's going to generate a file in your repo of this code quality analysis file. And almost the defaults are really pretty good. I really didn't have to modify much here at all with this file. The main thing that I had to modify was queries. So when this generates, it doesn't actually set what the query is that you should use. But I added the query that I wanted to use. There were some examples that were commented out, and I selected security and quality and uncommented that. And the other thing is that it actually needs to build your project in order to analyze it. And so it has an auto build capability, but that's not going to work with embedded. So it's not, the auto build isn't going to be able to build your project. I tried. But basically you can just run some steps, and you're running in a Linux environment. And so in this case, I basically just ran the steps to acquire Vcpkg, activated it with my project, and then ran CMake to configure and build, and then everything was wired up. And at that point, I can come back under the security tab here, and I can go to my code scanning alerts, and I can see a couple of notes. Like, so in this case, it found a couple of things that it's advising me about that I could potentially improve in my code. And I can, come in here and I can select one of these, and it'll highlight what the issue is, and I can, navigate directly to the file as well. So that's pretty cool, and it's highlighted when I navigate to the file as well. So this is pretty great. There was another project I ran that actually did find a security issue. So yeah, it's pretty good. The other thing I would note about this, though, is that you might be concerned about anybody being able to see this, but actually they can't. I'm logged in. If I were to use an incognito browser and come and look at this project, I could see the security tab, but I wouldn't be able to get to that code scanning report. You need to be authenticated and a member of the project in order to actually see that report. And similarly, if I am anonymous, I can come in and look at the actions, and I can see the results of the GitHub action flows, but I don't actually have access to download the artifacts. So you would need to actually take steps to publish your artifact if you wanted somebody to be able to use that. And so with that, let's get back over to the presentation. We're going to go fast through the next couple slides because they were really kind of backup in case I didn't have a chance to show that in context. But so, the slides really reiterate, get a container wired into the CI system of your choice, use multi-stage container builds, name your layers and use them as appropriate to get to that final build layer, which just which just runs and builds your project. And, as I noted, the challenge is going to be getting your chosen tools into the container. So it's going to depend on what your tool vendors provide in terms of being able to get them into that context. Unfortunately, a lot of these tools are provided in installers, which may make it difficult to do this. These were the steps in setting up the GitHub Actions. There's a little screenshot there of kind of the core parts of the ci.yaml that I showed you. But basically, you're just running the Docker commands in the context of the GitHub Actions, copying your build output, and then publishing it as artifacts, which I showed in context there. And then from GitHub code scanning, enable it under the security tab, update the YAML file for the query that you want to use. Auto build won't work, so add the steps to build your project, and then the alerts are going to show up under code scanning. I want to close with a mention of Renode. I didn't really talk much about testing or what you do with these binaries, but once you have the output of your build environment, you're going to want to deploy it to hardware, take it through some sort of validation. Renode is a pretty interesting environment that can help with this. Renode is an open source project that provides a simulation environment for CPUs, peripherals, sensors, and even networking. And what's interesting about it is it runs the same binary as the device. So the output of that build that I showed you that's a binary that would actually run on my physical device, you could actually take that binary and run it in context in Renode. And they've got a bunch of documentation on how you can actually run tests and everything. The whole thing is designed to be part of a CI system. Something that's really neat to take a look at is the screenshot there of the Zephyr validation board. So they're actually using Renode as part of the Zephyr RTOS project, which is open source, to validate a whole bunch of different platforms as they're evolving that project. And they're using Renode to kind of get some sanity testing around that as they're building all of that. So definitely a project that's worth checking out. And at that point, I think I can open it up to questions at this point. I think we made it to the end here with some time for that. The links for more information from this talk, that's a link you can hit that'll take you to a page I set up. A lot of research backed this talk, and there's links to everything that I used for that that you can find there. And that's a link to the sample that I showed that will take you back to the template project as well. And that's my email address if you want to hit me up with any questions after the talk or anytime. Opinions on Conan. I don't really have an opinion on Conan, to be honest. In my work, I'm working on the team that's working on Vcpkg. I know from talking with other folks in the embedded space that there are folks who have used Conan. In particular, I've talked to people who've used Conan, including acquiring tool chains and stuff like that. I have seen that. I've not studied it. I guess it didn't, the little bit that I looked at it, and I haven't looked at it recently, but when I did look at it, it didn't look very reproducible to me. It really looked like kind of, putting in scripts as part of your steps that could go out and actually do some of the things that we're doing through manifests and registries, but instead doing it through scripting that's part of the project that gets activated with Conan. That was my impression, but it's been a while since I saw it. If you've got other things I should look at, or examples to share, definitely drop them in the Discord. That'd be great. I think that to riff on that maybe a little bit more, I think kind of the next thing is to start figuring out libraries for the embedded space. We've really been focused on acquiring tool chains and getting the binaries necessary to build. And talking with most embedded folks, it seems like most people kind of cobble their projects together with grabbing the source code from a bunch of different places and building it as part of their project. It seems like, and Open-CMSIS seems like something that's really worth taking a look at to see, if we can get better than that and start being able to acquire things like from their source rather than, statically copying them into our projects. And I'm looking forward to trying to see how we can make library management better for embedded, leveraging Open-CMSIS or just figuring out better ways to use Vcpkg there, or learning from what others are doing around things like Conan or other projects. And PlatformIO, obviously I mentioned that one earlier. They've got a solution for library management. Nordic, yes. I didn't look at Nordic. Sorry, there was a question about if I've got any experience with Nordic semiconductor products. I don't. That was, I think, a gross oversight on my part in preparing for this talk, and I apologize for that. I have come across some stuff that Nordic is doing, particularly around VS Code, but I'm not familiar with it yet. I haven't had a chance to spend any time with it. And I'm also familiar with that, branching out of C++, I've heard, talking to people in the Rust community, that the Rust community seems to be focused on Nordic. So if Rust is of interest to you, Nordic might be a good part to look at, as well as Espressif. I think that those are kind of the parts that the Rust community is looking at. That's most of what I'm familiar with about Nordic, but yeah, I really need to improve my knowledge about what's going on with Nordic. And if you've got any references I should look at, please drop them in the Discord so that I and others can look at them. I'd appreciate it.